you want me to start?
I just started.
All right, welcome everyone. Thanks for coming out here. Hope the pizza was good. This is a good turnout. Welcome. If you guys haven't been to a mechanical engineering club meeting, please come out more. It only motivates us to do more programming for you guys. But anyways, this is Mr. Jack Haslin. He used to work for SolidWorks for almost 2 years, or more than 2 years. MakerBot, I'm so sorry.
Not a lot of SolidWorks customers.
At the end of the day, MakerBot, and then now he's running J3D, which is a 3D printing services company. And I'm sure he's going to talk more about it, but he's an expert when it comes to the world of 3D printing and how the technology has evolved today. And
We're good.
that's it.
We're good. Well, thank you, Kaiser. Hello. As Kaiser said, my name is Jack, and a really rude way to start a presentation is to correct your host, but I'm going to do it anyway. I'm not an expert on 3D printing. I do regard myself as a student of 3D printing, and the reason I make that distinction is I'm not really sure anyone in the industry today would qualify as a, quote, expert. The technology really changes day by day. The printers change, the filaments change, the applications change. So what I'm trying to do is keep on top of it, and I'll explain what I do, but I appreciate the thought of being called an expert, but it's probably a little bit over the top in my case. So before we get into it, my understanding is you have a couple of 3D printers here that you get some access to or some time with. Just by show of hands, how many people have used 3D printers? Good, excellent. Would anyone here say they've used one a lot? Or has anyone built one? Or has anyone had a few years experience with one? Anything at all? Okay. Well, if Mr. Reef wants to request a grant for a lot of money to spend on 3D printers, I can help him spend that. So, thought there. All right. So, why don't you go to the next slide? So, I'm not an expert, but most people know the name MakerBot. I assume you're all relatively familiar with that name. MakerBot is sort of the elephant in the room, at least as far as desktop computers go. And I did work there for 2 years. And during that time, it was really great. I got to work with companies like GE, Pratt & Whitney, and Toyota. Allison, you mentioned you did an internship with the Navy. I got to work with the Navy, the Army, the Air Force. Their 3D printing initiatives got to learn a lot about the applications they do. I mentioned the University of Maryland School of Engineering, because that's a really nationally ranked, like blocking anyone's view. That's a really well-known program around the country. And the Yale School of Architecture right down the road here, they have about 35 or 40 MakerBot replicators. Excuse me, so it gave me a really good opportunity to learn what the professional corporate world does in 3D printing. It gave me an opportunity to learn what the .gov, .military world does with 3D printing, as well as the educational world. If you're looking to get, and I'm going to talk about it a little more later on, this is a good book that I read recently. If you're looking to get an understanding of 3D printing and its implications, not just focusing on the technology, but just on where this is going in terms of job creation, applications, and so on. And then the 3D printing industry, that's a newsletter I subscribe to. It comes in every morning. If you want to get it, it's usually 8 to 10 articles covering all aspects of 3D printing, from the silly to the really serious. But it's just a good way to keep on top of things. So before you go to the next slide, this all looks really professional. I had that professional title, Trends and Implications. Another way to talk about this talk tonight is it's a real hodgepodge. Because, go to the next slide. Oh, I jumped ahead of myself. Oh, no, go ahead. What do I do? I left MakerBot in October of 2015, and I started my own company called J3D Services. I actually sell 3D printers. I also provide 3D printing services and 3D scanning, and I did that so I could simply, when I talk to groups of people, whether it's the corporate world or education, say, well, rather than saying, let's just talk about one 3D printing solution or one 3D printing resource, the purpose of J3D is to say, well, you need a printer, you just need something printed, you just need something scanned, and that's the company I started. And by and large, I work with engineers, designers, architects, educators, all people who have a need for some sort of physical representation of what they do. Yeah, I gave it a real professional title, terms and implications, but the talk tonight is a little bit of a hodgepodge. I don't really go into detail on the technology of the printers. It's more about what does this mean in terms of how we will design products, how we will create jobs, what does it mean for the business side of how companies basically work between their suppliers and their customers. So it's meant to be a broad topic. If that bores you, blame Alice, because I went over the agenda with her beforehand and she's fine. Let's get into it. Let's to the first slide here. So I worked for MakerBot. MakerBot makes what's called an FDM printer, fused deposition model. Very, very common, typically the low cost printer. But there are a number of 3D printing technologies. And this is not a set list. You shouldn't look at this list and say this is this category, this category, this category, because there are people within the industry who would say, well, this one can be combined with that one, this one's a subset of another one. But broadly speaking, these are the different ways that a 3D printer works, whether it's deposition modeling, which is just melting plastic and laying it down in a CAD file. There's laser sintering, where a laser binds together metallized powders. Laminated optic manufacturing, that's actually done with copier paper. Layer of adhesive on a piece of copier paper, put another one on it, keep cutting it out to the pattern. I'll show you an example of that in a second. And then this list of materials is incomplete. I could add to it every single day. But these are ones you hear of commonly. And I put glass there at the bottom of the question mark. Last summer, there was a company in Poland. I don't believe this is on the market, and I don't think they put a date on it. But they got the internal temperature of the extruder to about 1,600 degrees, and they started to 3D print bits of glass. That's a big deal. If they can get that to work and commercialize it, the medical and scientific applications for 3D printed glass would be endless. So this is a beginning list. Anyone who does 3D printing regularly would look at that and say, sure, we use this one or that one. But every day, there's a company in material sciences somewhere that's pushing the envelope on this. And these are, I could have picked any 7 or 8 images. These are just some that are kind of interesting. These are all done with a variety of 3D printing technologies. What really kind of pops out here is this is paper. Remember I said laminated object manufacturing? Layer of paper goes down. Adhesive, a layer of paper goes down, adhesive, and there's a very sharp blade, keeps cutting it out. From a company in Ireland called Quinnipiac Technologies. Because it's paper, getting the color is a lot easier. You know, it's like running a color copier or a regular printer. But there are geometries here. This one in particular, chair especially. If you worked in a traditional manufacturing environment, you start to realize that there are a lot of terrific designs that can't take place because of limitations of the tools. What 3D printing allows to happen, and engineers, industrial designers, they've known this for years, that there's more efficient ways to create a shape, you know, to work with it, but the tools have limitations, especially if you're trying to mass produce something. So now with 3D printing, you can start to make things that say, hey, we can push the envelope on this and make more efficient designs than we've ever been able to do before. So this is just a random sampling of it, and just to give you an idea of some very general diversity. Is anyone here very familiar with the history of 3D printing, or how long it's been around, or how we got to this point kind of quickly? Professor Reed is this gentleman here. Tell me something.
I know it's been around since I think like the 60s or the late 80s.
Late 80s. Late 80s, yes?
Yeah. It was one of those numbers.
I'm thinking you're older than your life. You're going to late 60s.
Yeah, no, it started in the late 80s.
Yep.
I feel like it's blanking on the rest.
It did start in the late 80s. The machines were very big. They were very expensive. They had expensive software licenses, and the material choices were very, very limited. And it had a really slow progression. But in the last 8 to 10 years, as technologies became more available, it really started to, there we go, it really started to develop. The rep community, and I guess people could debate this, but in my opinion, this is really what kicked it off. I'll say a little more than a decade ago, a mechanical engineering professor in London, or in England, I don't know if he was in London, wanted to do more with 3D printing. But the printers at that time were still big, they were expensive, not a lot of diversity among the materials, and he was like, I'm a mechanical engineer, you know, why don't I just build the thing? So he started, he wrote his own G codes. He learned about melting points, different filaments, different kinds of plastic. Started pulling together some gears and pulleys and belts. And he wanted to, his ultimate goal was actually not to build a 3D printer, but could he build a machine that would, in essence, make itself, which is where the term RepRap comes from, self-replicating rapid prototype machine or rapid prototype printer. And he put it all online. And thousands of people around the world in the coming years started to contribute to the design, contribute more, until eventually people said, yeah, these things work. And some people started taking them into their jobs, and then that's when startups like MakerBot, a guy named Bree Pettis in 2009, he and some buddies started to make kits. We went to South by Southwest, and the story goes, the legend is, he started printing shot glasses in the bar one night. And people were like, I want to get a machine that can print shot glasses. And he came back, and that was actually when MakerBot got kicked off. But it wasn't just MakerBot, it was this whole movement where people said, it is so handy to be able to say, I need to make something unique. I need to make a bracket, a jig, a template, an idea for a product. And I don't want to spend thousands of dollars going to prototypes and machine shops because I'm not sure my idea is going to work. So maybe I could just print it. This is just basic PLA plastic. It's about a 3-hour print. And walk into a meeting with fellow designers and engineers or architects and say, this is my concept. People can pass it around and say, yeah, but I think we need to change it here, here, and here. A few hours later, there's the next iteration. That really is where the value of a low-cost, easy-to-use desktop 3D printer comes in, and that's why over the last 4 or 5 years, this has really taken off. Printers are easy to use, they're not expensive, and people can share ideas quickly, get feedback quickly, change their designs quickly, and then get onto a finished prototype and put it into a working environment. The best feedback I ever got on that was from a fellow at Pitney Bowes. Pitney Bowes makes big mailing systems, mailing equipment. And he said, they have a fixed time of the year that a product has to get to market. So they know they only have so much time in the year to design the next innovation, to design the next iteration. But if you can do that much more designing in a fixed amount of time, you inherently get a better product. And that's what low-cost 3D printing allows you to do. More designing in the same amount of time, you get a better product. And that's really how it has advanced so quickly in a short amount of time. If you put your cursor here, you'll see that there should come up with a play button. Don't hit play just yet. When I was in MakerBot, GE First Build was a customer of mine. And they use MakerBot replicators. Hold on to these words. Constant innovation, multiple changes, see design quickly. This is about 2 minutes, and it's going to show you how a really elite manufacturing company, this happens to be GE Appliance, and this division First Build, what they do, instead of tooling up to make millions of dishwashers in a year or something, they try to come up with one product a month to launch. And then they get out to small retailers, maybe in a place like North Haven or Hamden, Connecticut, try to get a sense for it, try to do it every month, and maybe out of 12 a year, find one product to kick off the big GE Appliance and say, yes, this one we think has some legs to it. But they talk in here about how the 3D printing, how they use it.
Firstbuild was created as a way to get products to the market faster. Well, what's really hot now? That's what Firstbuild is supposed to see. The subsidiary of GE Appliances, but we're our own company. We have our own building, our own facility, our own rules and infrastructure, and we're out there trying to make products really fast.
Firstbuild is an incubator for a different way of designing products. The idea is speed, rapid development, build it, test it, try it, make mistakes, put corrections in. We're always wishing to go even faster.
We go to 3D printers as soon as we can, because that's the beauty of having 3D printing right there next to us. Is we've got an engineer sitting there making something and then printing it on a 3D printer. Why? Because it takes 30 minutes, a couple hours to print something.
It's a constant evolution process in our designs, and what we see by having the engineers and designers sitting in the next room with their 3D printers right in front of them, we get to quickly iterate and make design changes very fast.
We're using like this lean startup methods of actually putting things out in front of a customer and quickly iterating.
Pretty much every single product that we're working on right now, including the chill hub and the smart water feature, we're prototype on MakerBot. It's a good example of a product that we constantly iterated. The fact that we have 3D printers in our desks right next to our computer allows us to quickly make changes to our parts. So in a matter of a couple hours, I get to see multiple iterations of this part. And not only that, I can show them to my team. So it's a very fast way to iterate and design components.
The development time, cycle time has come way down because of all this new technology, 3D printing, rapid prototyping. You can try it out, see if it fits, see if it works, just building things in ways that we would never have imagined before.
Getting an idea from the community, turning that idea into a project, quickly iterating. This is what we're in right now. We're in the middle of it right now.
We are very fond of this saying that says a prototype is worth 1,000 meetings. What we're basically doing is every time we print a component, we're having a meeting. So it's not even a meeting, it's just a discussion. And we get to make the changes basically instantly.
There were certain key words they said in there. They can design quickly, they can make changes quickly. If you're trying to get a product to market, you have a deadline. So this is the exact same thing the fellow from Quinnipiac said. That gal Amelia, she said, we go to 3D printers as soon as we can because it helps the design process so much. Now, go to the next slide. This, unfortunately, somehow I lost the feed on this. This video doesn't play. But down in Greenwich, there's something called the Whitby School, and they were trying to get 3D printers in the hands of the kids, and just to see what they could do with them. And they started to create something called Whitby Harbor, which I have a picture of in a bit. And the kids are doing very simple boats and very simple houses and painting a green piece of plywood and making this Whitby Harbor. But if this play, I'm sorry we lost the feed, this is a couple years old, so Bruce here, I hope he's no longer in 6th grade. Hope he graduated and moved on. But he said, on his own, he's been using the 3D printers, and he says, first think of an idea, make multiple versions, evaluate which one. He was in 6th grade. And then continue pushing it further until it is perfected. Now, go to the next slide. And this is really pretty extraordinary. So Tomas Garces of GED is saying constant innovation, multiple changes, see design iterations quickly. The kid in the 6th grade make multiple versions, evaluate which one is best. They're kind of saying the same thing. Using, I put a MakerBot replicator here because I happen to know both sides are using the MakerBot replicator. I couldn't put in any desktop 3D printer. If you work in the engineering field, you go to work for a company that makes something, whether you're on the factory floor, you stay on the design side, over time, you'll become familiar with things like CNC machining. Do you have a CNC machine here? Okay, so CNC, no? Yes, no?
We have a partial
Okay.
CNC. We do a limited amount of CNC. You can go, you can either run it in a manual mode or you can run it in a CNC mode.
Got it. So, but as you work more in a production environment, again, whether you're actually on a shop floor or whether you're staying on the design side, you become aware of manufacturing process. You know, CNC machining, lathes, forges, injection molding. Now, there are no 6th graders who know anything about those things. He knows a lot about them because he works with them every day. But what's really kind of extraordinary about desktop level 3D printing is you can put the same tool in the hands of both of them. These guys don't know each other. One's in Greenwich, Connecticut, the other's in Louisville, Kentucky. One's a grown man, one's a boy. And with the same tool, they can both use it, and on their own, come to the same conclusions. That is an incredible level of teaching. You couldn't have done that before. So the fact that these guys are learning the same thing with the same tool is really unique. And the next slide. So this section began with why 3D printing? Why now? Why is it coming along so quickly? Again, this is a MakerBot replicator. It doesn't have to be. But there's a woman in New Jersey who told me about these. And I didn't believe it at first until I started to snoop around. I would have thought, okay, you probably could get exposed to 3D printing like that boy when you're in 6th grade, certainly junior high, school, college. And she said, no. There are kids in 1st, 2nd grade who can go into something really simple like Tinkercad. Tinkercad is a free online CAD program, works with basic manipulations, basic shapes, and they can figure out about fraction blocks. So here's half of something, here's a quarter of something, and the kids start, they create a cube in Tinkercad, and they cut the cube in half, and they cut the half in half, and then they go print it, and it helps them understand the relations between fractions. You can actually get this down to a 64th. I didn't really feel like printing 64 little blocks. But I thought, no, that's really interesting. I didn't realize there were applications that at that young an age, could benefit from 3D printing. Then you get to Whitby Harbor. Those kids are like in 6th, 7th grade. This was really interesting. It was out in Newton, New Jersey. Apparently there was a girl who has some sort of congenital disability, and she doesn't have full use of, I don't know if it's her right hand or left hand, but the lockers in that particular school, it's a high school in Newton, New Jersey, apparently you need both hands to open up the locker. And a couple of boys, I think they were juniors, they have a 3D printer in the school. On their own initiative, they went to one of the teachers and said, we would like to figure out a way to make it easier for this girl to open up her locker. And they went back and forth for a few weeks, and they had her help involved. Well, I don't quite know how it works, but they came up with that red handle, and it mounts over the components that you normally have to use 2 hands for. And now this girl with this disability has a much easier time opening her locker. This came from a student at the University of Minnesota. I didn't know, how many people here knew, that we share 80% the same DNA with zebrafish. And you didn't know, John. You're saying you didn't. I learned this up at Pfizer. I did a little bit of work at Pfizer up in Groton, and zebrafish are used a lot in drug research. I never would have thought this would be an issue, but apparently, for a long time, when they feed zebrafish and they're trying to put in an amount of a drug they're testing and researching, getting precise amounts of the food and the drug has apparently been difficult. Now, to me, that was the kind of thing that would have been worked out years ago. But this kid at the University of Minnesota, using a 3D printer, figured out a way to make a gun or a dispenser. Gun's a dirty word, I guess, in 3D printing. A dispenser that they can precisely put in the amount of fish food and the drug, and they know exactly how much they're feeding the fish. And I said to the fellow up at Pfizer who told me this, I was like, how did you do it before? He was only kind of eyeballed it. So I'm like, really? And then we get back to Tomas Garces at GE First Build. The question was, why has 3D printing taken off so quickly? A big part of that answer is the versatility. Grammar school, middle school, this is a college student, but again, they do it now at actual pharmaceutical companies, engineering companies, but it's all the same tool. It's all the same resource, and it's not hard to use. So that's really why it's taken off so quickly. It's the versatility of the resource. So on that earlier slide, and I had a whole bunch of pictures up there of different sorts of products and things, there were some designs on there that you couldn't do with traditional manufacturing methods. We're at the very beginning of this now, and it's really kind of exciting that whether you're an engineer or an industrial designer or an architect, you can start to take shapes that will be a lot more efficient than what we've been able to use in the past, and then you'll have a way to make them. So, is anyone here familiar with this? This was actually, a couple of years, 3 years ago now. The Grad Challenge that GE Aviation did. Does this ring any bells with anyone? This was really interesting. So, GE wanted to redesign the bracket that's on a jet engine so they could make it lighter. Make it lighter. GE has all these metrics in place for making their jet engines lighter using 3D printing over the next 5 years. And the bracket is really important because when the jet engine is finished, it's got to be picked up, it's got to be mounted on the wing, and then for basic maintenance, at times it might have to be taken off the wing. So these brackets are really important, and they have to be strong in such a way that the engine doesn't lose its shape. And of course, they have to be strong enough to hold it. So what they did, and I think it's on the next slide, they worked with GradCAD. My understanding is they didn't expect to get anywhere near this many entries. But there were 700 people around the world who entered this challenge to come up with a better designed bracket. 700 people across 56 countries. These are just a very small sampling of some of the designs they got. And they had to put them through all kinds of testing. They had to see which ones are going to work here. And then they got to this fellow here in Indonesia and shared the wine on. I hope I said that correctly. And this was the bracket. He's not even a GE employee. This is the bracket he designed. It has to be able to hold an engine, 12,800 pounds. The original bracket that they were using was about 4.5 pounds. That design lowers it, makes it 84% less. That might not sound like a big deal if you're just talking about 4 pounds. But a jet engine, there are multiple brackets on the engine, it's not just one. The jet engine should be in service 25 to 30 years. Over time, that could save 1 million gallons of fuel, maybe even a few more. And then they take that technology and put it into other components out of the jet engine to keep making it lighter. This is, could you make that in a traditional manufacturing environment? Yeah, you probably could. But there'd be a lot more points of failure to it. It'd be so complicated to make it any kind of CNC environment. And it wouldn't be structurally sound. But with a 3D printer, you can put the strength where it's needed, you can keep it light, and now you do have a way to make it on an ongoing basis. So that's one example of, that's probably the kind of design that somebody might have known for years would have been a better way to do it. But there was no way to make it. This is one that I really find interesting. So in architecture and construction, you need a way to bring your steel beams together with trusses, your joinery work. And this is a very standard component provided to a node, structural node. Probably 1 million of those or some variation of those around the world in buildings everywhere. But the issue with them is, again, this is just because of the way our manufacturing tools have worked, there's a lot of material here that isn't needed, but it was a cost-effective way to make it. That you can easily weld. So what this particular company did, I thought I had the name on here. They're a global engineering consulting firm. They said, let's look at these structural nodes again. Let's put them through the kind of analysis where we can say, we only need material here, but not here. We need strength here, but not here. And they went from this iteration to this one. So finally they got to an even smaller one. It said, what is it, 75% less, only half as high. What I love about this picture is this looks like something completely man-made, obviously. I think, in my opinion, these two look like something that was wrong. And what an engineer pointed out to me once, a fellow who's been a mechanical engineer for 35, 40 years, he said they all understand the best designers are in nature. You walk through nature, you don't see shapes like this. You see organic shapes that are a lot more efficient. But we don't know how to make them. And now, there are ways to make them. There are materials to make them. So you say, yeah, we don't need all this anymore. And we need to make it more aesthetically interesting, at least from an architectural standpoint. Next one. Okay. Before you play that, this is a really boring 37-second video. Just bear with me for 37 seconds. Now, it's going to do the same thing here. This is a NASA test for fuel injected from last July. This is as exciting as it gets. Not going to be more than that. You overwhelmed yet? Demo, 3, 2, 1. So that was a testing of a 3D printed NASA fuel injector. But what did you really just see? Go to the next slide. That fuel injector was spinning at 90,000 RPM, generating 2,000 horsepower. If it had run for a full minute, if that video is a full minute, it would have delivered 1,200 gallons of liquid nitrogen per minute at minus 240 Celsius, generate up to 35,000 pounds of thrust. A really big one. Even though that fuel injector is a few hundred parts, if it was made with traditional manufacturing processes, it would use about 45% more parts. And the reason I bring that up is there are people I meet, and I'm always very surprised at this. There are people I meet who are engineers and architects and other folks who have backgrounds who use 3D printing, but they still think of it in terms of simple plastics or materials that can make a variety of shapes and they're really big. They don't necessarily understand yet that it can be used in some really, really extreme environments. How many environments are more extreme than having to go 90,000 RPM, 2,000 horsepower, move a fuel at minus 240 Celsius? So that's a tremendous achievement. And last October, and I just found this out recently, I don't have a video yet, they actually test fired the whole rocket. Also, much of it made with 3D printed parts. So all of this, from an engineering standpoint, is really great. And again, it's things that they probably couldn't have done or done not nearly as efficiently with traditional manufacturing process. But the reason I point out this last one, this is what I said at the beginning, so it talks a bit of a hodgepodge. We've talked about printers, we've talked about some of the materials, some of the applications, but what does it mean? What is this real 45% fewer parts? Well, NASA doesn't have to get a part to market at a particular time, but as 3D printing becomes faster and more familiar how to use it, that can have enormous implications. So what's the impact on business if you start to design your products and produce them? Lots of companies design with 3D printing. Not a lot yet have 3D printing in production. But we've just seen that 3D printing can withstand some incredible environments. So what if that starts to change? Well, the impact on business, supply chain management, the world runs on supply chains. We all know this. Products move around, 1 million products a day move around the world in ships and trucks and ports. And broadly speaking, they come from China or they come from, Massachusetts to Connecticut. But we all move. The supply chain is the lifeblood of how every company works. Whether you're a supplier to your customer, they make a product that goes on to their customer, and of course you have to buy from your supplier. Supply chain management is huge. It's how everything works, from toothbrushes to jet engines. Now, we saw before in that slide, I had one 3D printer, I had all those applications around it. And now we're starting to get to the very beginning of what they call digital fabrication centers, where there are locations that have a variety of 3D printers and some scanners and some laser cutters. And these are machines that don't need to be retooled. They can, you can make an application here that's medical, they can make an application that's aerospace, they can make an application that's architectural, all of the same equipment. So if these digital fabrication centers take off, and I think they will, then you end up with a supply chain that is much more regionalized and has a much lower carbon footprint. So this hasn't happened yet. We're at the very, very tip of it. You probably have heard of companies like Shapeways. Yes or no, maybe not. Shapeways is a service bureau. Sculptio is a service bureau where you can upload your designs to them. They will print them and send them to you. But it's, you know, they're just running with 3D printers. They can do any design. So in this one location, you can have multiple products and multiple needs produced. I think that model is going to diminish where it becomes much more localized. You know, why couldn't New Haven, Connecticut be a 3D printing hub? And Hartford, Connecticut be a 3D printing hub? And then one in Providence, one in White Plains. What does that do to the supply chain? Well, this is huge. So if you go to the next slide for a second, this is a very, very simplified diagram of a typical supply chain model. And this is really simplified. But your raw material suppliers who these suppliers buy raw materials, these suppliers buy from these suppliers, they produce a laptop which goes out to a wholesaler, a retailer, finally to the end customer, nice and neat and clean. It doesn't work anywhere near as simply as this. I mean, just on the supplier side, you have to negotiate terms. You know, the supplier wants to get paid in 30 days, this one's okay with 45 days, this one wants a letter of credit. I mean, it gets really, really complicated. And then every one of those activities is repeats itself every step of the way in the supply chain. Then you turn around and you sell to your customers. And somebody comes along with a technology, sticking with the NASA model, and says, you know that product you've always made? We think we can make with 45% fewer parts. How many of these suppliers do you still need? You're going to need some, but you won't get all of them. And what does that mean for how businesses do business? Go to the next slide for a second here.